Hi, so this is the second lecture in our recorded lecture series on the mathematical prerequisites for quantum mechanics. The broad subject of this lecture series is linear algebra, and today we are going to look at a very important aspect of linear algebra, which deals with what are called inner products. So you can think of inner products as just being a generalization of the concept of a dot product that you're familiar with in your usual physics courses. So this is like a dot product. Why is the dot product so important in physics? It so the dot product has a lot of applications. For example, given any vector v, if you want to find the quote unquote length or magnitude of the vector, that is given as just v dot v under root. There's a special name for the length of a vector, it's called the norm of a vector. So here's how you calculate it. If I want to calculate the angle between two vectors, so if I have vectors v and w, you know that v dot w is just and this is sometimes denoted as mod v. That's the magnitude of the vector. So v dot w, you know, is given by magnitude of v times magnitude of w times cosine of the angle between them. So you can find this angle as the dot product divided by the lengths of the two vectors, and we already know how to calculate the length in terms of the dot product. So if you want to write it explicitly, this is so in terms of the dot product, you get the angle between any two vectors. The dot product also allows you to find out what is the component of a vector. How? So suppose I have a vector v, which is given by, in our old physics notation, vx I hat, vy j hat, vz k hat. And let's say I ask you, find out what is the y component of this vector. So the way to do it is to take the dot product of this vector v with the basis vector along the y direction, which is j hat. So what will this give you? This will give you vx I dot j plus vy j dot j plus vz k dot j. And notice that I dot j is 0 because these two vectors are perpendicular to each other. K dot j is 0 because they are perpendicular to each other. And j dot j is 1 because it's a vector of unit length. So what you have in the end is vy. That is what we wanted. We want to find out what is the y component. So in general, for any vector, if you want to find out a certain component, you can do it by taking the dot product of the vector with the corresponding basis vector. So these are the reasons why the dot product is actually very useful in any kind of physical calculation. And what we want to do is we want to generalize the idea of the dot product and write down what is called the inner product between two vectors in any vector space. So we'll start as follows. Remember, we were using the notation in which we were denoting our vectors as these kets. And now what I'm going to say is that for every vector v in the vector space, I'm going to say there exists a dual vector which we denote with this pointy bracket pointing the other way, and we call it the bra. So if you think of the ket as having some components like this, a1, a2, an, this is in the column notation that we wrote down last time, then the corresponding bra you can think of as being the row vector, a1, a2, an, and not just by transposing it and making the column matrix into a row matrix, but you also have to complex conjugate it. So this is in some sense a way of defining this dual vector or the bra vector corresponding to V. And then we define what is called the inner product of any two vectors V and W as this. Let's write it. So let's say this is V, and then I have another, let's do this properly, this is V, so the bra of V is a1 to an complex conjugated. Similarly, let's say there is a vector W whose components were b1, b2, bn, and so the bra of W is defined as b1 up to bn complex conjugate. Then the inner product of bra V with ket W is just the matrix product. So bra V is a1 to an complex conjugate, and ket W is b1 to bn. So if you do the matrix multiplication, you will find that this is a1 conjugate b1 plus a2 conjugate b2 and so on, an conjugate bn. So this is the inner product of V and W. Here I am assuming that the field over which these vectors are defined is the complex field. So all your components a1, a2, an, b1, b2, bn, all of these are complex numbers. So I'm working with that understanding. If we are working on the real field, then they would make this doing complex conjugation doesn't really make any sense. So we would just have taken the transpose to go from the ket to the bra, and then our inner product would have been a1 b1 plus a2 b2 and so on plus an bn. This is exactly like the dot product that we do in physics, no? If you're working with Cartesian coordinates, then you take any two vectors, their dot product will be given by vxwx plus vywy plus vzwz. So same way over here, except we are generalizing it to the complex field. Now I've called this the inner product. There is actually a more formal definition of the inner product. Or rather defining properties, I will call them. Defining basically what I'm saying is that this way of writing the inner product is not unique. You can in general construct any kind of inner product you want. Given any two vectors, you can make your own prescription of how to take an inner product between them, provided that inner product satisfies certain properties. So we are writing down those properties now. So inner product. So let's say I have inner product of two vectors v and w. Then the inner product has to satisfy the following properties. if I take the inner product, then this has to belong to the field over which the vector space is defined. So in our case, the vector field is just complex numbers, but in general it could be real numbers or any other field that you're working on. So this is one. The second property is that if I exchange the order, so how is V, inner product of V and W, related to inner product of W and V? That is the question. They are related to each other as complex conjugates. So if you flip the order of the two, then your inner product should get complex conjugated. Let's check the third one. The third condition is that the inner product of any vector with itself must be a real number and it must be greater than or equal to 0. So it has to be non-negative. Because intuitively you can think of inner product of V with itself as being the length of the vector. So length of a vector cannot be a negative. You always want it to be a 0 or a positive number. And in addition, the limiting case when it is 0 is only possible, so if and only if V is the null vector. So it's only for the null vector that its dot product with itself or its inner product with itself should be 0. All other vectors have to have a non-zero norm. That's what we are saying. And the last property is a distributivity property. So if I take the inner product of V, not with just one vector W, but with some linear combination of two vectors. So A1 W1 plus A2 W2. Then basically the constants come out. So I can write this as A1 VW1 plus A2 VW2. So these are the 4 defining properties of inner products. Let's check if the inner product that we wrote on the previous page satisfies these 4 properties. So over there we wrote V dot W as being, what components did I call it? A and B. Okay. A1 star B1 plus AN star BN, where the AIs are the components of V and BIs are the components of W. Okay. Is this thing a complex number? Yes, it is, because all the AIs and BIs are complex numbers. So when you multiply them and add them, you get a complex number. Very good. If I take W dot V, will it get complex conjugated? Let's see. W dot V means I have to take bra of W and ket of V. So this becomes B1 star to Bn star and then A1 to An, which is A1 B1 star plus An Bn star. And you can see that these two are just complex conjugates of each other. So yes, the second condition is also satisfied. Third one, if I take the inner product of V with itself, so V with itself is going to be A1 star A1 plus An star An, and this is just A1 star A1 is just mod A square, A1 square mod An square. And yes, all of these are individually non-negative numbers, and therefore this entire thing is also a non-negative number. All of these are 0 or at most 0 or positive. So when you add them up, you still get a number that is 0 or positive. And notice that if you want this to be 0, then individually all of these numbers will have to be 0. Or in other words, V is just the ket 0, 0, 0, 0. So that is the null vector. So that condition is also satisfied. Similarly, you can check the fourth property also, that will also be satisfied. you can distribute the inner product over the ket. So therefore the prescription for the inner product that we have written on the previous page is valid. This is a valid inner product. Okay. One thing I want to stress over here, we have checked what happens if you distribute it over the ket. What happens if I distribute it over the bra? In particular, suppose I want to take this inner product. So W over here, but over here I want a linear combination. So I want to put, let's say, A1 V1 plus A2 V2. Then what happens? Okay, let's see. Now, from the second property, this is just going to be complex conjugate of the flipped. So if I just do this, and this we know from, so this has come from property 2. From property 4, we know how to expand this out. So we know that this is A1 WV1 plus A2 WV2. And now I can take complex conjugates. So this becomes A1 star. But star of WV1 is just the flipped. So V1W again from 2 plus A2 star, and inner product of W and V2, when I complex conjugate it, it just gets flipped. So I get V2W. So you can see, if I take A1 V1 plus A2 V2, again this also distributes, except that those coefficients A1 and A2 get complex conjugated. So when you're distributing, whenever you have some numbers sitting on the right hand side, on the ket side, they will distribute as usual. But when you have numbers sitting on the left hand side in the bra, then those will get complex conjugated when you distribute. Okay. All right. So let's look at some more examples and check what can be an inner product and what cannot be an inner product. So let's take an example. So on R3, okay, this is my field. Let me take R2, actually it's easier. So I'll take some vectors, let's say, so R2, so just two components, A comma B, let's say. Just two component vectors. I want to check if I define V comma W as AB times a 2 cross 2 matrix, let's say 1 1 2 0 C D. If this is my definition of the inner product, question is this a valid inner product? So basically for this definition, so this is a definition. For this, you have to check if this definition satisfies those properties that an inner product ought to satisfy. These ones. So does the inner product belong to the field? Yes. If you, so this is a 1 cross 2, this is a 2 cross 2, and this is a 2 cross 1. When you do matrix multiplication, you'll end up with a 1 cross 1, which is just a number. So yes, this belongs to the field. If I flip the order, will it get complex conjugated? Well, that is irrelevant over here because these are just real numbers. But question is, will the value remain the same? So that you can check. Is VW equal to WV. So VW is, by definition over here, as we have written, AB times, what is this, C plus 2D and D. I'm just doing matrix multiplication. So this becomes AC plus 2AD plus BD. Similarly, if I do WV, I will end up with basically A goes to C and B goes to D. So I will get AC plus 2BC plus BD. Is that right? Yeah. And clearly these two are not equal to each other. Therefore, inner product of VW is not the same as inner product of WV. Therefore, this is not a valid inner product. Okay. Good. There's also one more property I think which will not be satisfied. If I take inner product of V with itself, I will get AB 1 2 0 1 AB, which becomes A square plus 2AB plus B square. So A plus B the whole square. And you can check. So this, okay, I agree that this is always greater than or equal to 0. But this, if this is 0, it doesn't mean that V is a null vector. Because even if B is minus A, this will still give you a 0 norm. So this also is not satisfied, which can be 0 even when V is not the null vector. So again, not an inner product. Let's take one more example. Again on R2 only. So again, I'll take my vectors and I will define it as follows. And question is this a valid inner product? Okay, let's check. So VW is 2AC plus 3BD. If I take W comma V, basically I'm interchanging A and C, I'm interchanging B and D. So I will still get 2AC plus 3BD. So okay, I have verified that the symmetry condition holds. Inner product of V and W is the same as inner product of W and V. I don't have the complex conjugate because it's over the real field. This is definitely a real number, so the first condition is also satisfied. Third condition, I have to check norm of V. So V with itself is going to be 2A square plus 3B square. And yes, this is always non-negative. And if this quantity is 0, this can only be satisfied if A and B are separately 0. There's no other solution. So therefore V has to be the null vector. The fourth property, distributivity, you can check that will also work out. So therefore this is a valid inner product. It may not be a very useful inner product, that's why we don't define an inner product like this, but strictly in the formal sense this is a valid inner product. Let's take one last example, and here I am moving on to the infinite dimensional vector space that we spoke about the last time. This is the vector space of functions defined on the interval 0, L. Yeah, so the vector space of functions defined on the interval 0, L. How do we define an inner product on this? So suppose I take any two functions f and g, belonging to this vector space, and then I define the inner product as integral from 0 to L of complex conjugate of f times g. It turns out that this is actually a good definition of an inner product. Wait, why is my video halting? Right. So integral from 0 to L f star into g, and you can check that this is a valid inner product, because for this one this integral, when you do this integral, you end up with a complex number, so it belongs to the field. If I take f g and if I take g f, if I interchange the two, it's obvious from the formula, you can see that they are complex conjugates of each other. If f comma f, if you calculate it, this is just integral 0 to L f star into f dx, which is 0 to L of mod f square. Mod f square is a function that is always going to be positive, therefore its integral over this interval is going to be a positive or non-zero number. And if this turns out to be 0, it can only happen if the function f is identically 0, so f has to be the null vector. And distributivity also works. Because this is just therefore this is also a valid inner product. And whenever we are dealing with the space of functions, this is the inner product that we are going to use. Two quick definitions. One we have already seen, which is the norm or the length or the magnitude of a vector, and this is defined as the length of v, and this is just square root of the inner product of v with itself. The second definition is the definition of orthogonality. Orthogonal means the two vectors are perpendicular to each other. We say that v and w are orthogonal to each other if their inner product is 0. So any two vectors whose inner product is 0 to each other, is 0, you will say they are orthogonal to each other. Okay. One statement I want to make at the end of this particular video, and this is for those of you who are more inclined towards pure mathematics. I never formally defined what this bra vector means. I said at some point that there is a dual vector, but what this dual vector means I never said. Turns out that you can define a whole other vector space called the dual vector space, and these bras are actually vectors belonging to that vector space, and the inner product then becomes an operation which takes a vector from your original vector space and a vector from your dual vector space and operates on them and gives you a member of the field. So formally, for mathematicians, that is how you would define the inner product.